Hi there, my name is Roshan. Welcome to Tech with Whiteboard. On today's video, we are going to look all the problems of coordination Republic Day Drive, and we will see the approach to solve these problems with a better time complexity. All the codes can be found in the link in the description, and while you go check out the code, please give a like, share with your friends, also and click on the bell notification so that you do not miss any of our videos. So without further ado, let's get started. So our first problem is hard problem. What this problem simply says is that there will be a list of t numbers, and you have to figure out whether the number of distinct divisors of that number is prime or not. What I mean by that is, suppose a number like 100 is given and its prime factorization is 2 square 5 square. So number of distinct divisors this number has as distinct 100 is 2, cause it only has 2 and 5 as divisor. So you have to tell whether this number actually is prime or not. So in simple words, if is prime distinct whatever number you put here and is true or not. So in this case, for 100, we know that 2 is prime, then print yes, else print no. So this will be the logic. Now writing in terms of pseudocode, let's just write in terms of pseudocode. We can clear this. In terms of pseudocode, our pseudocode look like this. Suppose we have a function, and I'm using Python as programming language, but the codes can be found in all three different languages: the C, C++, Python, and Java. So if you want to follow up, you can click on the links. You can click on any of the links given below, and you'll find our code. So we will write our function as distinct, and it receives n. This is returns this returns distinct prime divisors of n. And we have another function is prime. It takes n and returns whether n is prime or not. Once we implement these two functions, the final function is simple. We simply say if is prime distinct n equals to true, then we print yes, else we print no. So I'll be focused on writing code. I'm going to pause my video. As you can see, first we will take all the test cases, and then we will take our number. According to the pseudocode, we can see we have to write this block. So we will write that block. Distinct prime factors, and then we print yes, and else we print no. So fair enough, all we have to do is implement those functions. As we know that n is around 50 and n is around 10 9. So constraints on the problem is n equals to 50 and now we will use let me finish writing code first. So is prime is okay. So if n was divisible by 2, we would return false. Else we divide by return true. We will use the same kind of logic here as well. We simply say distinct count. We will maintain the count. So if n was divisible by 2, we will change the count by 1, and we will do the same thing, but first we will divide n by 2 as long as we can so that n is free of 2, and we do the same thing again. And this is our complete program. Test one. So let's see where we are. So it's time to do a little explaining. If you are new to prime factorization, then I'm going to explain how this works while the time complexity is less. Or if you already know about it, you can click on this time stamp and go to the next problem. So the way prime factorization works is, suppose you have n. If n is prime, then you simply return yes, it is a prime. But if n is composite, say 100, then you can find its first prime divisor, whatever the lowest prime divisor of n is less than equals to root n. What it simply says is the smallest prime of n that divides n, pi divides n, and pi is the smallest, then pi is less than equals to root n. And we use this fact in figuring out how the prime factorization works. So for example, say if a number like 1001 is given, if you take its root, then it will become around say 33. Let's say 33. If what it means is that there is one prime divisor that divides 1001 if it is composite. So what it means is it can be divisible by 2, 3, 5, 7, 11, up till 33. Let me clear more space here. So let's say you have 33 and you all the primes up till 33, that is 29, 31, can divide 1001. We know that its prime factorization is actually 7, 11, and 13. So as you can see, 7 does lie below 33. So yeah, it works. How we utilize this fact is we look for all the numbers that is less than root n. So any divisor, say we are factorizing 100. So if 100 was divisible by 2, which it is, we can check by doing 100 modulus 2 equals to 0. We will make 100 devoid of 2 because you know it already divides 100 by 2 and you are only interested in counting different prime factors. So why not get rid of all the 2's in 1,000. So it is 2 square and 5 square. So this line of code will get executed. uh, this line, if n is modulus 2, we increase the count and we divide n of 2, and then we move on. We say 3. Now the number after being divided of 2 is 25. We do root 25, that is 5, and we look for all the divisors less than equals to root 25, which is the same as saying take the square here and remove this. So div square is less than equals to n, and that's what the next loop is about. Div square is less than equals to 1. Observe that we start with 3 and we increase by 2 because 4 and 6 can't be a divisor of 100 because we already got rid of all the 2's there. So we jump by odd numbers, and it takes half as much time because we are not looking at all the even numbers. So this is the answer to the first problem. It will be in the description. You can download from there. Let's move on to second problem. The second problem is like this. The kingdom of Asgard is ruled by King Odin. So basically here what happens is the simple problems in, you can read the problem here. The problem in simple language says that uh, if there is a number arrangement, let's say like this, n is 4, then all of the numbers that are greater than everything that's on the left gets promoted. So 1 has nothing on the left, it gets promoted. 2 has nothing on the right, it get 2 has 1 on the right actually, but it is bigger than whatever is on the left, so it gets promoted. 4 is greater than everything that's on the left, so it gets promoted. But 3 is not greater than everything that's on the left, because 4 is greater than 3, and hence 3 is not promoted. So you basically want to know the expected number. Let me get on that. You can find the expected number as total promotions it's better. Total promotions across all arrangement permutation will be about of n divided by n factorial. This is our answer. So let's take an example. Let's say n is 2 and our arrangements are 1 2 and 2 1. Here both gets promoted, here only one get promoted. This can't get promoted because it has a bigger number on the left. So there are total three promotions across all arrangement, and 2 factorial divided by 2 factorial. This is our answer, 3 by 2. That's how we calculate expected value. Let's take a better example, this time of 3. So let's say n is equals to 3. Then your all the arrangements are 1 2 3, 1 3 2, 2 1 3, and 3 2 3 1, 3 1 2, 3 2 1. Now let's say which of them gets promoted, right? So we will make a table here whether one got promoted, or let's keep it this way. We have a table here who got promoted. Let's say 1 got promoted, or 2 got promoted, or 3 got promoted, something like that. So in the first row, everyone gets a promotion, and hence the total is 3. In the second one, only these two guys get promotion, and he doesn't get a promotion, so total is 2. Similarly, we will figure out promotion in all of them. So here only this guy gets promoted and this guy gets promoted, and here both of these get promoted. Let's count them: 2 2 1 and 1. Total is 3 2 2 6 3 9 11. 11 divided by 3 factorial 6. This is our answer, and we will simply calculate 11 into 6 inverse mod 10 to the power mod whatever modulo given. Our answer will be 11 into inverse 6 mod. You can look on internet how to find inverse of a number, but how do we do that? So I'm going to erase this one here. See, ask yourself how many times 3 gets promoted. So 3 gets promoted here, 3 gets promoted here, 3 gets promoted here, 3 gets promoted here, 3 gets promoted. It would seem like 3 always gets promoted. So 3 gets promoted 6 times. How many times 2 gets promoted? So here, okay, this is wrong. Actually, this is not column for 1, 2, 3. This is simply what 1 was here promoted, 2 was here promoted, 3 was here promoted. 1 was here, he was promoted. 3 was here, he got promoted here. So this one would mean 3, right? And 2 is here. So just match. So 2 didn't get promoted here, 2 gets promoted here, promoted here. No promotion, no promotion. So 2 only gets promoted 3 times, and 1 gets promoted 2 times. So the question is, how can you find this number if I give you how many times I gets promoted? If n is say 10 and I is say 4, so across all arrangements, how many times 4 would get promoted? So this is actually very easy to come up with. Like, the only way a number would get promoted by definition is if everything on its left is small. A number I would get promoted is if everything on its left is smaller than I. Right? Simple. So what we will do is we will make n empty spaces. Say n is equals to 4. We will leave that there. Or maybe we can take the example of 4, it's 3 itself. So observe that 2 can't be here because he won't get promotion there, because there are only one number that is smaller than 2, or basically I minus 1 numbers smaller than I. So if there's more than I minus 1 spaces here, 2 spaces, then he won't get promoted because you end up using a number bigger than 2. There are not there are simply no not that many smaller numbers than I. Okay, so if, like for example, just take n equals to 4. So if n equals to 4 and you make something like this, then you can't keep you can keep 4 here, but you can't keep 3 here, because there are only 2 numbers smaller than 3, smaller than 3, and you have to fill 3 places, so you end up using a bigger number. what you can what this means is a number I a number I can only take a place with position a number I can take a place with position less than equals to I. So if you want to keep 3, it can be here at third place, here at second place, and here at first place. And if you want to keep 2, 2 can be here and here, second place and first place, but it can't be here. So Let's say if you take a number I, then there are I minus 1 smaller numbers. I'm going to delete for more space. So let's say you have this many positions. You chose a number I at kth position, and so there are k minus 1 on the left and n minus k minus 1 position on the right. So these are like blank fields. What you can do here is that you have I minus 1 smaller numbers. So you can take I minus 1 permutation k minus 1. Just take k minus 1 numbers from the small I minus 1 smaller numbers, and whatever number is left on, you can do the factorial there. So the sum goes from, say, sigma. This is for the kth position, but remember I can acquire all the positions. The k can go from 1 to I can acquire all the k positions such that k is like this. So what you can do is you can do sigma k equals to 1 to I, and this is only for the ith number. uh, if you want to solve it for every number such that I goes from 1 to n and k goes from 1 to I, and this is what you evaluate here. So let's just sigma k equals to I equals to 1 to n, and give all the proper places to k, and you evaluate this one. So just copy paste from here to here, then whatever this comes out will be your numerator. So for n equals to 3, let me just write it there. It's not I minus 1 p k minus 1 into n minus k minus 1. When you solve this, you will get n factorial you will get n factorial sigma k equals to 1 to n 1 by k. I hope that's visible. You will get n factorial sigma k equals to 1 over n 1 by k. So this will be your numerator. What this will be for n equals to 3 is I'm going to delete upper portions, is that for n equals to 3, when you solve this, you will get this one, which is 3 factorial 1 by 1 plus 1 by 2 plus 1 by 3 which will be 6 plus 3 plus 2 or 11. And if you divide by 3 factorial, you get your answer. So if you divide by 3 factorial, this would cancel out and this will be your answer, which is a harmonic series Hn. So our answer is Hn. The proof for this fact will be given in the description. You can download from there. Let's move on and I will show you our code. So this is our code. Very simple. We take n and we define our mod. We are simply calculating h0. So what we do is we simply want the answer of. I'm going to delete everything here. What we're simply calculating is 1 inverse plus 2 inverse plus n inverse as given mod, which is 10 to the power 9 plus 7. And we are basically saving it in the array, which we don't need here. Let me show why. You can simply take n and you can see your answer is 0. Just go from 1 to n and add to your answer inverse. So this is how we take inverse in Python. Mod minus to mod, and we added this. Also we will take the mod and we will define our mod. So as you can see, the code is not very big, it is small, but it's only about the thinking and the proof. You can get the proof in the description. So without further ado, let's move on to the third problem. And if you have any doubts, please leave a comment below so that I would know. Let's get on the third problem. The third problem is basically saying, in simple words, that given a string, say a b b a c d e e d c, find the longest palindromic substring. So you can find the normal palindromic substring code on internet. It's very easy, but the caveat here is that there can't be it can't be like this. So a can't be followed by a until it's the junction. I mean, it's the middle it's the middlemost character. Until it is the middlemost character, you can't have uh, consecutive uh, values. Like this is okay, because a gets followed by b. It can't be followed by a until it is in the middle itself. So what it's simply saying is that mirror images are allowed. We are simply finding the longest palindromic substring, so that the one half of it, there is no consecutive letters that are same. So this will be bad. This will be bad, because I mean, even if it exists in the string, you have two letters that are same. So you need to find something like this. So we just improve our code. We simply say what is the longest palindromic substring in ij, such that previously it was a. What I mean by that is, suppose uh, suppose we find, let me get rid of this value. Suppose we have something like this: a b b a c c. Very bad handwriting. a b c c b a. So if you run the normal palindromic substring, it will give you the whole substring. What we do is we compare two last characters ij, and if they are equal, we say give me the longest palindromic substring in this a region from I plus 1 to j minus 1. But here we will also send one more value that it can't start with a. So you see, when the normal palindromic substring works, it gives you the whole substring length, because it there is no constant that it can't start with a. So you define your dp like this: your dp I to j, like what is the longest palindromic substring in I to j inclusive, such that previously it started with a letter prev. So basically what here it would say is give me dp, how much is this, 0 to 7 or some previous is the same dp 0 to 7, and previous is basically a dummy character because there is no previous word for the long for that range 0 to 7. Basically it's saying give me 0 to 6 such that previously it was a. So what your palindromic substring and what your new function would do is give you from give you your palindromic length from b to b. It will ignore that a because previously it was a, so it would ignore consecutive rings. So what you would do is check a and say please don't start with a, so it starts with b, and that b in turn will say okay, give me the longest substring in this smaller range, but don't start with b. And see, there is no b, so it starts with c. Let's look at the code. So the code is not uh, very weird. I am simply using LRUCAC for memoization purposes, and which basically means is that I don't have to define dpij and prev to save values, to save calculated values. It automatically does it. So to more about that, you can search online. So as you can see, the function is very simple. There are It's a recursive function. There are edge cases, like suppose you give me to find substring in 10, there is no substring in 10, so it will return 0. Also notice that we are only interested in even length palindromes. So every odd length palindrome is 0. I mean, they are bad. We are not considering odd length palindrome because we need to take the mirror type, something like this, according to the question. A B A B A B A. So as you can say, if I is equals to j, then it is of length 1. Either it is bad or of length 1. So we return 0. If they match, like here, then we make sure it is not equals to your starting point si is not equals to the previous value. So in case of, like, say our input was s equals to a b c c a c c b a, then it would simply say run on function 0 to 7 and previous is star. It will go inside and check that s0 is same as s7. So, and also s0 is not star. so it can move ahead. S0 is not star, it is actually A, and then it will say, now give me a palindrome in, find me a good palindrome in, say 1 to 7. Basically saying, find me good, better palindrome in here. So I'm ignoring this one. I'm not considering palindromes starting with this or having potentially started here. Or I'm saying, give me a function palindrome in 0 to 7, 0 to 6. I'm basically ignoring this one. And I'm making sure they don't start with A. So I would send something like this. And it would give me the required palindrome. So I save that length in R, whichever is maximum. Also, what I can do is I can ignore both of them and say, give me the largest palindrome here such that it doesn't start with A, which is which is which is what I did here. Pre is S. You can change your pre here actually with SI. You can change your pre here with SI because you are considering that you're considering both of them, you're letting both of them in, so you're saying that one of your palindromes does have A, so please don't start with A. Let's run it to make sure it works properly. A B C C B A 6. We can see it gives 6. If we didn't change that here, it will give us 8. I mean, that's the bug in that code, right? So just make sure when you're considering both the left and right ones, so you make sure that the inside palindrome doesn't start with SI, and that's about it. This is the code. So the questions are like tough, but the code is very easy. Let's move on to the fourth problem, which is actually my favorite. Let's actually run that code. I wrote that in just to make sure it works. F5 ACBD EA ACDB DEA 4. So we can say we have matches sample output A D D A. Let's start again with A B B A C D E E D C 6. So it matches sample output. Again, let's move on to fourth problem. We can also check taker. So taker would be easier. Taker is 0. Let's move on to fourth problem, which is my favorite. And this one I would explain in detail because I tried to figure out the solution on the internet, maybe on CodeChef or on Discuss, but I didn't see the solution. So I would explain this one very in very much detail. So let's start with what is a diameter. So suppose you have a tree like this, then diameter is the longest path. Let me write here. Diameter is the longest path in the tree between any two nodes that belong to the tree. So basically, what is the longest path that you can cover going from one node to the other one? assuming that you only traverse along an edge at most once, just once. So you can't do something like this: go this way, go that way, go that way, go that way. So in this case it will be 4, but you traverse this one twice, so this is bad. So let me just get you a better tree. Just join them, call them 1, 2, 3, 4, and 5. So what happens now is that, what is a subtree? A subtree is basically you fix the root, or no need for that. Basically this can be a subtree: 3, 1, 2. So you do not change the structure of the tree, you just delete some of the previous nodes with their edges. So you get a subtree or a subgraph. And you want to know that across all subgraphs, what is the frequency of diameters across all subgraphs. This is the question actually. So all the subgraphs you can get by simply saying that you deleted everything below here. So your subgraph is 1 and its diameter is 0. So let's make our frequency table here. Actually something like this. So you can get 0, 1, 2, 3, and 4. So this is dia and this is frequency. And by the way, this is not needed by the question. You only have to print the lower ones, only this much information from 1 to n. But for the sake of simplicity, we will keep there. So all the possible single nodes, 1, 2, 3, 4, 5, they all have diameter 0. So if you have a subgraph like this, where you deleted everything but left 1, so that is 1. You have there's a possibility that you only left 3 and deleted everything, so that's also 1. Then there's a possibility that you deleted everything but left 2, that is also 1. In total you will get 5, because there are 5 lone nodes. Similarly, for getting 1, so you can get 1 diameter like this. Keep 1 and 3 and delete everything here. Delete this. So that is 1, and this one's 1, this one's 1, this one's 1, and that's it. So you can get 1 in 4 ways. Similarly, you can get 2. Similarly, you can get 2 like this. This is one of, just delete this thing here, and in this tree you have a diameter of 2. So that is one subtree that has diameter of 2. And similarly, delete everything here, you will get 2 again. Similarly, delete everything here and you get again 2. Just keep on doing that here, and so how many ways you can get 2? Let me just, instead of calculating it the brute force way, let's just run it into a program to see what it would give. We have 5 nodes. One is connected to 4, one is connected to 3, 3 is connected to 2, and 3 is connected to 5. So 4, 5, 3, 0. We have 4, 5, 3, and 0. This is what we will get. 4, 5, 3, and 0. So let me just say how this is 1, this is 2, uh, this is 3, and this is 4, keeping this and deleting everyone. And we want one more. How do you get one more? 1, 2, 3, 4, and 5. Which one is the fifth one? Let's see which one is the fifth one. Print subset. Here we're increasing diameter, so we will see what diameter went to what subset. Cancel. 5, 4, 1 to 4, 1 to 3, 3 to 5, 3 to 2. So 2 goes in 1 to 3. So 1, 2, and 3, that is 1. This one. And it goes in 1, 3, and 4. So it goes in 1, 2, 3, 1, 3, 4, 1, 3, 5. So we have 1, 2, 3, 1, 3, 4, 1, 3, 5, and 1, 2, 3, 4, 5. 1, 2, 3, and 5. Okay, this is also the tree that has diameter 2, right? Because we're just taking one node. So one of the trees is like this. The second tree is like this, subtree actually. And we have one tree like this, 3, 2, and 5. We have one tree like this, 1, 3, and 4. So that's 4 in total. The fifth one is basically 1, 3, and 5. So just do 1, 3, and 5. They all have diameter 2. That's why the frequency is 5. So the question is, how do we, like, deleting nodes? Deleting nodes is not optimal. So if you keep on deleting nodes, randomly, and seeing whether it forms a tree and what is its diameter, it's going to take you a lot of time. So what we have decided to do is observe that n is 20. So you can write exponential time algorithm for this. And you can do that. You can simply say 2 to the power n. 2 to the power 20 is around 10 to the power 6. Not very bad, actually. 2 to the power 20 is 10 to the power 6. 10, simply 10 lakh for 48,000 something, but yes, workable. So what we will do is, our idea is, say n is 5 given, we will generate all the subsets. So let me show you what we mean by a subset. We'll simply print the subset here and we'll get rid of this. Don't focus on the code. I will get to everything. Just focus on what's happening. So I am basically entering the tree every time. I, sh I should have just copied it. So these are all the subsets. You know how to make subsets. The elements of the subset, the element of the set is 1, 2, 3, and 4 and 5. And it's basically making all the subsets. The total subsets are 2 to the power 5, which is 32. You can see here, from here to here, there are a total of 32 subsets. So we get that subset using a technique like this. We get that subset using a technique like this. See, we start, we say this is a mask. For mask in range, we start with 1 because we don't want an empty subset, and we end at 1 to the n. Just let me print this to show you what's happening. N is not defined, obviously. That's what's happening. So let's keep this 5, and that's it. You can see 1 to 31, all of them are present, and 0 is the 31, 5th element. But we are not interested in empty subsets for this problem. If you wanted empty subset, you can simply keep 0 here. Let's also, instead of printing mask, let's print its binary decomposition. So let me show you what's happening. Don't focus on the code. I'm just making it more prettier to appear on the screen. Just focus on what's happening. As you can see, this is the binary number of all the numbers. This is 1, this is 2, this is 3. All the ones denote that that number was taken. So basically what 00011 means is that if the number was 5, 4, or if the number was 1, 2, 3, 4, and 5, then we took 4 and 5 because that is 1 and 1. So that makes the subset. For this number, we are taking actually 3, 4, 5 and ignoring this. So 0111 would denote this subset 3, 4, 5. What we can do here is basically Z fill 5, and we know this is our binary number, and we will see what kind of subset we get. For I in range 5, if I is open, if I is open means 1, then you just append to it the value. Note that this is 1 index, this is 0 indexed, and we want 1 index thing, so I'm just increasing by 1. And you can print the subset Z fill. As you can see, we are getting all the subsets. So either you write it this way or you write it this way. There's no difference. It's basically that 5 comes later, and I still have
all the subsets. So what this does is, you can look online, it basically checks that the power of, the ith bit. Suppose mask was like this, mask is 00111, and you do 1 2, you are basically doing 1 2. So this will return true if the second bit, this one, if the third bit, actually this one from the left, was 1, means set. In this case this will return false because the third bit is 0. And basically, like saying 0 means that is the first place, or the first bit is 1. In this case this is return true. If you do 1, this will say this bit is on, and it will return true. So instead of like running a loop and checking what the binary number in string is, you can also do masking. Masking is just a bit faster than storing the string, because bitwise operations are done on the CPU, uh, very fast. So this is how we check the subsets. Now, not every subset is a good subset. So not every subset is a good subset. Let me show why. Suppose your subset comes 1 4 and 2. So you're basically saying, ki you are assuming that 1 4 and 2 forms a tree, subtree, but this is not possible, because to have this, you need to delete this, so when you delete this, the bridge here, or the connection here, gets broken. There is nothing that connects 1 and 4. So a set like 1 4 and 2 is bad set. Bad set or bad subset, because it can't form a tree, because it is not a subtree. The question is, how can we find which subsets are good? Like, we know 142 is bad, but 143 is good because they are connected. If you delete everything else, if you delete this, they will still remain connected. So we will get to that. Assume you can figure out, assume you can find which set is good or bad. Assume you can find which set is good or bad in n square time complexity, which is, I mean, doable, because n is 20 at most, so very doable. We'll get to that. Now, once you have figured out uh, how to find the how to find whether a good subset, and whether it is a good subtree or bad subtree, how can we find diameter in that subtree in n square time? Again, that is good, because n is very small. So for this, we will do computation. We will figure out, on the original tree, find all the find all pair shortest paths. This is what we will figure out. So there's a, you can look online, there's an algorithm for this, which we will use. Algorithm is Floyd Warshall. So Floyd Warshall works in V cube, and V is not very big. V is say 20. So 20 into 20 into 20. That's also workable. You only need to do one pre-computation. So let's start with that pre-computation thing. This was for masking. Suppose we will take our tree in adjacency list. You can find code in other languages in the link in the description. But for now, just bear with me. This is actually an adjacency list, and you will get it. The default tick is basically so that I don't get key error. And here's my graph, which is an adjacency list. And once you have n, I need to take the graph, which I will do here. So for edge in range n minus 1, because there are n minus n edges, just take the edge and form the graph. So just to see u dot append v and do gv dot append u. Once you have the graph, you want all pair shortest paths, which is easier to get. Just initialize your cost. You can look for the float Warshall algorithm online. Um, do something like this. Just have a 2D array and run the standard Floyd Warshall algorithm. So I will copy this because I'm lazy. And you know how Floyd Warshall works. You will simply say cost I to k, cost k to j, and your cost I to j is always minimum cost I to j comma k. You're basically saying minimize my cost of traveling. I will call this I, call this j, and also this will be way above here, and it won't start with 0, it will start with float infinity. Right now the cost is wrong because that's not how costs are defined, but for the time being we know that the only paths that are connected are 0. I mean, if you print right now without doing anything, your cost will look like this. So if you don't do anything and 1315, that's not how it was. 1513143532. As you can see, your cost is infinity, but the cost the cost of traveling from the cost of, I mean, the distance between 1 and 3, which is an edge which will be given, is 1. So while we are making our tree here we can also fix the cost. So you can say cost uv is 1, and apparently cost vu is also 1. Now once you fix that cost, and damn, I keep forgetting. Great. So you get some of the nodes as 1. So traveling between them, say this is 1, 1 2 3, 1 2 3, traveling 1, or the diameter between 1 and 3 is 1, like the distance, minimum possible distance between 1 and 3 is 1, which is what Floyd Warshall does. We can get rid of more infinities by saying that cost u to u is 0, because traveling to your own node doesn't hurt, and v to v is 0. Now if you do Floyd Warshall, and after doing Floyd Warshall, you look in the node, you look in the matrix, then you would see that most of your paths are fixed. So traveling from 1 to 0, 1 to 1 is 0, 1 to 2 is 2. So traveling from 1 to 2 is definitely 2. Now this is the minimum path. I will get rid of most of the things here. So now you get it. We are basically computing what is the minimum cost if I want to go from here to here, how many edges I have to cross in the minimum time. Now, now the way we solve this problem, let's look. I'm assuming you have got it. This is basically cost is a 2D matrix which basically says cost ij minimum edges between I to j in original tree. So how do we figure out whether a given subtree is good or not? That was my problem. So once you have figured this out, and let's say 142 is given, you would run two loops, something like this. Once you get the subset, you would run two loops. You would say 1 to 4. What is the cost of traveling from 1 to 4? If it is 1, you increase your counter. You're just maintaining counter how many costs you have, such that how many costs in that two loops you have, such that your edge differences are 1 or the cost is 1. So let's look at the original code once, since you're done here. What I will do is figure out the length of subset, and I will run two loops. So like this, and j is basically one ahead. I'm basically getting a pair of indices. That's what I'm doing, and I'm getting the numbers there. So I'll simply say what is subset I and subset j, and I get their cost. So if cost uv is 1, if cost uv is 1, means this is an edge in the tree. So basically uv is an edge, like it was given when you were running when you got the input. So if this is an edge, you basically say edge count is plus equals to 1, and just maintain the edge count, just maintain the edge count. If edge count is equals to ln minus 1, which basically means number of if edge is 1 less than number of nodes, then it is a tree by definition. By definition. So what would happen is, if you are getting 1 4 and 2, you will say that 1 4 edge is 1, cost is 1, so edge count is 1. 4 2, between 4 and 2 the minimum distance is 3, so edge count will remain 1. And between 1 and 2, 1 and 2 edge count is 2, so edge count will remain 1. So total number of edges that belong originally to the tree is like this. Let's say if you are given 1 4 and 2, you are assuming that there's an edge, whether there was an edge one between 1 4 1 2 and 4 2. So if there was an edge, their cost will be 1, but if there wasn't an edge, their cost will be more than equals to 2. So your findings indicate that the only edge that is here and here is this one, but you need at least two edges to form the tree because there are three nodes. and you need two edges. So this subset is bad. It can't form a tree in the original. It can't form a subtree from the original tree. So this is what I do in my original method. See, this is what I run to make the graph. This is basically for cost. You can ignore this and look on the current one we have written here. I will show you which subsets are good. Let's just print which subset is good. We will get rid of that cost. We don't want cost. Actually, we do want cost. And for practical purposes, I am omitting the zero row and zero column, because the rows and columns were one zero based, but we want one based. So this is our cost from 1 to 1, from 1 to 2, from 1 to 3, from 1 to 4. And these are all our good subsets. 1 to 3, 1 3 is also good. They are connected. 2 3 is also good. They are connected. 1 to 3 is also good because they are connected. Like 1 is connected to 3. 4 is good. 1 4 is good, and others are good. So as you can see, these are the only good subtrees. So if we figured that out in one square time complexity here, running two loops. Now if it is a good subtree, the current subset forms a good subtree. Then what is its diameter? That's what we are about, and we were storing the frequency of all all the nodes, which is basically 0 into n, frequency of all diameters from 1 to n minus 1. That's what the question asks. Here you can see frequency of 1 to n minus 1. So what we will do here is, what is its diameter? We can find the diameter actually. Diameter is the longest path in the tree. So if this the longest path is basically maximum distance between maximum diameter, that is you already have, and the maximum distance between u and v, that will be our diameter. Right, to keep on iterating around the pairs and see which pair are the farthest ones, and you'll get the diameter. And here just increase your diameter's frequency by 1. So you have computed it. Just run a loop from 1 to n. I hope our n is good. No, it's not good. And print frequency I, and n is not defined. Where did we use small n? Here. Here you go, 4 5 3 and 0. And cost is basically not needed to be shown. So I hope you get it. The only troubles here were like how would a subset, how can you say a subset is a part of that original tree by deleting subnodes? So you for that to happen, all the nodes need to be connected, and all the nodes in the subset needs to be connected, and that would require you n minus 1 edges, or exactly the size of the subset minus 1 edges. And for that many edges, you need the cost of any two nodes in the subset pair like this one to be 1. So suppose you take this subset 1 3 4 and 5. Let me explain once. And you make all the pairs. So I'm removing this one. If only I had more space. See, if this is your subset and you don't know, it can be in any order. Order doesn't matter. So you make pairs. So you do 1 3 1 4 1 5 first loop iteration, 1 3 1 5 second loop iteration, and 3 5, and you figure out all of their costs. So 4 to 1 is 1, 4 to 3 is 2, 4 to 5, and they are pre-computed, so no, we don't have to figure out at runtime. 1 to 3 is 1, 1 to 5 is 2, and 3 to 5 is 1. So the number of ones here must be exactly length of subset minus 1. And that's when it will form a tree. Think about it, why this needs to happen. Because if it is 1, it was an edge in the subtree. It was edge in the original tree. And if it was an edge in the original tree and this edge exists in our current subset because we can make pairings, and so then we can connect. So let's just see, it says 4 and 1 is 1. So in original tree they were connected. And then you says 1 and 3 in the original tree, the cost is 1, so it means it was an edge in original tree, so you can connect them. And then you say that 3 and 5 are connected, and hence you have all the nodes that are connected and all the nodes belong to that subset. So I hope you're getting it. You can figure out whether a subset is good. I mean, it will form a subtree, or and if it forms a subtree, then what is its diameter, all in O(n) square calculation. So the only thing that is left is to prove the time complexity that it will work. So what we are doing is we are running first loop that finds this that finds the subset. So we do 2 to the power n subsets. Now let's not look at this. 2 to the power n is same as, let's say, 5 is the same as finding one subsets, finding two subsets, and so on till finding 5 subsets. And obviously 50 is missing here, so don't worry about it. It only factors in 1. So if you have an r size subset, then you require r square extra uh, r square here, r square looping to find whether it is a good subtree and what is its diameter. And so the total time complexity is sigma n square r square, and uh, this will be uh, this will be around, let's say r goes from 0 to n. Damn, it is not even visible. Sigma n r square, and r goes from 0 to n. And it's not exactly r square, it's actually r2 because you make only r2 pairs by running that loop. You can apply Newton's identity and write it like this: n2 n minus 2 r minus 2. And now you can solve this one. So the total time complexity will be, total time complexity is n2 2 to the power n minus 2, which is workable because it's not very much. If you do 20 into 19 by 2, that is 22 190, and 2 to the power 18. So at worst you need to do this many computations, which is around 4 into 10 to the power 8, 10 to the power 7, I guess. How much is this? 4 4, yeah. So 5 into 10 to the power 7 calculations you need to do. around, which is very workable. So I hope you like this video, and I hope you like this video. And all I want to say is that more problems from lit code weeklies and other coordination problems will also be posted online within few days. So if you really like this video, please please share with your friends who are still stuck on the problem, and you can even subscribe and press the bell notification so you do not miss any of my videos. Thank you for watching, and now I will take my leave.